All right, well, that's officially 6:30, so we might as well get started. Uh, like I said, with 10 pages of practice questions, I don't know if we'll finish them all, but I will try my best. So first one is draw a correct structure according to the following compound, R2-bromo-5-ethylheptane. If I were doing this, honestly, what I would do is draw a heptane, and 2-bromo means the bromine's going to go here, 3, 4, 5. There's an ethyl group here. And what I would do is put the bromine on a wedge bond and the hydrogen on a dotted bond and see if it's R or not. I have a 50% chance. And if it's wrong, then we'll just switch them. So that's what I would do. Might as well make it easy on myself and put the H on a dotted bond. So the bromine's number 1. Then comes the long alkyl chain, the CH2. And then comes the methyl group. And lo and behold, that's a right turn. So there's our answer, R2-bromo-5-ethylheptane. If that had turned out to be S, I would just switch the H and the Br. That's how I would approach it. Sometimes you don't have to worry about whether you can figure it out beforehand. Just try one and see if it's right. And in the worst case, you have to switch it. Next question. When excess 2-methylhexane shown below is treated with chlorine and irradiated or heated, several monochlorination products are produced. Draw any 4 of them. Well, what you do is you work your way down the chain, replacing hydrogens with chlorines. So the first one is over here, unless you wanted to start on the other side, which you certainly can. That's a possible answer. Then we'll move the chlorine down 1 carbon. That's another isomer. Then we'll move it down another carbon. And then we'll move it down another carbon, and then we're done. It says draw any 4 of those monochlorination products, but I'll draw all of them just so you can see them all. We can also put the chlorine between the 2 methyl groups. And last but not least, we can put it on either of those 2 methyl groups. It doesn't matter which, all 6 of those hydrogens are the same. And I think that's it. So that's how to approach a problem like that. You just start at one end of the chain, replace the hydrogen, could be a chlorine or a bromine, because this could be Cl2 or Br2. But if you're asked to draw isomers, just be systematic. That, I think, is the best advice I could give you. Any questions so far? Now for the R and S. So first it says to circle all 6 chiral carbons. Well, here's one. That carbon is 4 different groups. This carbon also has 4 different groups. Of course, the carbon on the benzene ring is not chiral. It's sp2 hybridized. And then there's one over here that is 4 different groups. That one is 4 different groups. That one is 4 different groups. And finally, that one is 4 different groups. So those are the 6 chiral carbons. Now, in order to figure out whether they're R or S, I don't know if we'll do all of them. We'll put our H's in over here. Whoops. That's very nice. Both of the H's are on dotted bonds. So let's assign priorities. It says assign an absolute configuration of R or S to any 4 of those 6 carbons. The answers are, of course, in the answer key. But the first priority is going to be the nitrogen. Second priority is going to be this carbon that's got a double bond to another carbon. And the third priority would be this one, the CH2. So that looks to me like a left turn. This carbon is S. As for the next one, the first priority group is going to be this benzene ring. Well, wait, is that true? That carbon is as though it has bonds to 3 other carbons. One, two, three. This carbon is also as though it has bonds to 3 other carbons, because the double bond counts as 2 carbons. So then we get, if we go around once more, we get to this carbon, and then we get to the carbons with the chlorines, which are going to take priority over all of these carbons, which have no chlorines or any other heteroatoms attached. So I think the first priority group is this one. Then the other aromatic carbon. And finally, the CH2. And that looks like a right turn. So I think this one is R. This one also has the H in back. So the first priority group is going to be the nitrogen. The next one is going to be the CH2. And the third priority will be the CH3. So 1, 2, 3, that looks like a left turn. So I think this carbon is S. I'm just going to take a quick peek at the answer key and make sure I'm doing these right. Oh, that's right, they're all S. So that means that I've assigned this one wrong. And I think I know why. The reason is the first priority carbon is this one, because we never get to the chlorines. So these two carbons are a tie. This one and this one are a tie. When we go around once again, this carbon is as though it were attached to 3 carbons, but this carbon is only attached to 2 carbons, as is this one, because of the double bond. So that means this one is priority 2, and this one is priority 3. That one was tough. But they only had to assign 4 of the 6. So this one is actually S. I think I'll also do this one, which is the hardest one of all. Let's verify that this one is also S. So I think the first priority group is going to be the CH that's attached to a nitrogen. Then the CH that's attached to a carbon. This is attached to 2 CH2s over here and over here. And third priority is this CH2 over here. And indeed, oh, that's a right turn, but notice the hydrogen is on a wedge bond, not in a dot bond. That means even though it's a right turn, we change our mind at the last second, and we say this one is S. So that's how you do that. I actually have an idea. I don't want to do this question. I want to do one that I think is going to be better preparation for you. Since we don't use that style of drawing structures very often. Let's say we were given this compound instead. This compound has 2 chiral carbons, so there's a maximum possible of 4 distinct stereoisomers. So same type of question, draw all of the stereoisomers. One of them would have both of the bromines on a wedge bond. Another would have both bromines on a dotted bond. So your 4 possibilities are up, 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 down, up, and down, down. So we got up, up, and down, down. This one is up, down, and then we got down, up. And those are the 4 possibilities. So again, just be systematic about how you do this. If you see 2 chiral carbons, then you can have a maximum possible of 4 stereoisomers, unless there's a meso compound. Here we're not going to have a meso compound because I don't see a plane of symmetry anywhere. So all 4 of those are distinct stereoisomers. Boy, it seems like so long ago that we did chapter 5, but this is all chapter 5 stuff. And then we need to assign R or S to all chiral carbons. Clearly indicate, this question says, clearly indicate any pairs of enantiomers and write meso under any meso compounds. So once again, why not make it as easy on yourself as possible? Let's assign R and S to this stereoisomer, since both hydrogens are on dotted bonds. So we'll look at this carbon first. Of course, the bromine is first. Then comes the carbon attached to the bromine, and then the CH3. That looks like a right turn to me, so I'm going to call that one R. And then we need to assign this one. Bromine is, of course, going to be first priority. Then the carbon with the bromine attached will be second priority. And finally, the CH2 will be third priority. 1, 2, 3 going around this way. That's again a right turn, so I think this one is R also. I'm just going to make sure I'm right. This is going to make you very jealous. I have a command for show stereochemistry. There it is. Yep, they're both R. Now, once we've made the assignment on one structure, we're done, because we can get all of the others by comparing to that structure. So if that one is RR, this one must be SS, since it's the enantiomer. This is a diastereomer. This one would be RS, because the first chiral carbon has the same stereochemistry, and the second one is opposite stereochemistry. And this one will be the enantiomer of that. This will be SR. So bottom line, if you're given a structure like this and asked to draw all of the stereoisomers, systematically go through all of the possibilities. If there is only 2 chiral carbons, which is how we did it in class, then you're going to have 4 possibilities, and you just need to make sure as to whether there's a meso compound or not. And you can tell if it's a meso compound if there's a plane of symmetry. And there is none here. That means all 4 stereoisomers will be distinct. And then as for figuring out R versus S, pick the easiest one. Pick the one where both hydrogens are on dotted bonds. Do that one first. And then you can get the other 3 stereoisomers by comparing to that one. And then it says, indicate clearly any pairs of enantiomers. These 2 are enantiomers. And these 2 are enantiomers. Any other pairing would be diastereomers. And there is no meso compound. So that's, I think, how to approach a problem like that and solve it the quickest way possible. Good. Make sense? Any questions on that? And again, I am recording, though I don't know when I'm going to be able to get this up on YouTube, because I'm in meetings all day tomorrow from 8:30 to 5. Then I have something going on in the evening. But the latest I will get it up on YouTube is after class on Wednesday. I'll try to get it done tomorrow. All right, this is an active style mechanism question. That means we just need to supply all the arrows. It says carbon-carbon pi bonds undergo many other addition reactions with electrophiles. Several other such reactions have the same kind of mechanism as we learned for the reaction of ethylene with HCl, HBr, or HI. And we learned that any alkene, not just ethylene, any alkene reacts with HCl, HBr, or HI by that same mechanism. So that's a mechanism we went over extensively in class. It makes sense to expect that mechanism is going to show up on the exam in such form. We spent a lot of class time on it and did several examples. This one is a reaction with methanol and a catalytic amount of acid. So remember, the first step involves the pi bond reaching out to grab a proton off of the acid. So that's what the first step looks like. The first arrow looks like. And then we also need to break that oxygen-hydrogen bond so that the hydrogen doesn't have 4 electrons around it. And that makes sense. Putting those 2 electrons onto the oxygen gets rid of the plus charge. And we're left with a molecule of methanol. So we have a carbocation. This bond has swung away from this carbon, leaving a tertiary carbocation, which you'll recall, tertiary carbocations are in the same manner as tertiary radicals, the most stable type of carbocation. And the reason is this one, tertiary carbocations have the most electron density around them. The carbons have much more electron density around them than hydrogens do. So this is a particularly stable carbocation, though we will have more to say about carbocations in chapter 7. So when we compare this structure to this structure, we see that the oxygen is attached to the carbon with the carbocation. And this is where in the reaction with HCl, HBr, or HI, we would show Cl minus, Br minus, or I minus attacking the carbocation and forming a bond to that carbon and getting rid of the plus charge. Exactly the same thing happens here. So we start our arrow at the oxygen because that's where the electrons are, and we point the arrow at the carbocation carbon. And you'll see we wind up with a new carbon-oxygen bond, and this oxygen will now have a plus charge on it. So there is just one other step. So compare this structure to this structure. And you'll see that what's happened is we've gotten rid of this hydrogen attached to oxygen. That means something needs to deprotonate that oxygen. Something needs to take H plus away to get rid of the plus charge in oxygen. And that something happens to be a molecule of methanol, which you're given right here. So the methanol, remember your arrow always starts where the electrons start and ends where the electrons end. And the electrons are going to start at the tail of the arrow and form a bond between oxygen and hydrogen. That electron pair and the lone pair on oxygen is used to form a new oxygen-hydrogen bond. And then we're not quite done yet. We also need to break this oxygen-hydrogen bond. And I'm a little bit limited on chem draws I can't always draw the arrows quite like I would like to. But we break that hydrogen-oxygen bond and we put the electrons onto the oxygen with a plus charge. That gets rid of the plus charge. And you wind up with this structure. So these first 2 steps are exactly like the reaction with HCl, HBr, or HI. The only difference is this 3rd step, which is a deprotonation. So that answer with those arrows received full credit. All of the structures are given. All it needed was arrows. Good. I hope we actually do mechanism with HCl, HBr, or HI, since we talked about that a lot. If not, I'll make up an example. But that's one type of mechanism question where you just have to supply the arrows. Other times you're given the starting material and the product and you have to supply the entire mechanism. And there should be some questions like that. Actually, I'm going to skip this question because there's another one just like it, except you also had to draw the initiation and termination steps. So we'll leave the propagation step out. No, we won't, actually. Remember what we said in class. Yeah, let's not skip this. Let's do the propagation step since that's the hardest one. Remember what we said in class. If you want to know which H to take off of the starting material, look where the halogen is in the product. And that shows you where to take the H off. The halogen is over there on that carbon. So that means in the propagation step, it's that H that we're going to remove with a radical. So here's our chlorine radical. We need half arrows now. Fish hook arrows. And the chlorine's going to donate 1 electron. We'll get 1 more electron from the CH bond. That's going to come together with that one and form a new bond between hydrogen and chlorine. We'll make an HCl molecule. And then the second electron in the CH bond will go onto carbon, and we'll get a carbon radical. After the first part of the propagation step, you should always get a carbon radical. Always. There are no exceptions. Wish that dot were a little bigger, but that's the radical that you get. And then recall that the radical reacts with a halogen molecule, not a halogen atom. It's always a halogen molecule. So we draw a fishhook arrow from the radical to in between the carbon and the chlorine. We take 1 electron from the chlorine-chlorine bond. And remember, this could just as easily be Br2 instead of Cl2. And we take that 1 electron and we join it with the single electron from the hydrocarbon radical. And then the second electron in the halogen-halogen bond goes onto the halogen radical. And you get a molecule of the product plus a chlorine radical. And that's basically it. So just to make things as clear as I can, I would say everything that I showed here needs to be shown. Anything I did not show here does not need to be shown. like I didn't draw the HCl molecule. You can show it if you want to, but you don't have to. So that's how to draw a correct propagation step. You can expect that will be on the exam. We did a number of examples of this in class also. So remember, the propagation step has two sub-steps. In the first one, we break the carbon-hydrogen bond, and we already went over how to tell which carbon-hydrogen bond. You need to look where the halogen is. That shows you which carbon-hydrogen bond to take. And then that carbon-hydrogen bond will react with either a chlorine radical or a bromine radical, depending on which halogen you're given. And that gives you an organic radical. That organic radical then reacts with the halogen molecule, either Cl2 or Br2. A very common mistake here is to take another halogen atom, not a halogen molecule. That's not a propagation step, that's a termination step. So be sure that you use the Cl2 or Br2 molecule here. That gives you the product that you expect, plus another halogen radical. That halogen radical will then go and find another hydrocarbon molecule, making a radical, which reacts with the halogen molecule, making the product, plus another halogen radical, which finds another hydrocarbon molecule, and so on. That's the chain of the radical chain reaction. And that keeps going around and around and around until you run out of Cl2 or Br2, and then the reaction terminates. Now, which of the following describes the carbon attached to the chlorine in 1-methyl-cyclopentane? That's the carbon attached to the chlorine. And I would say that is a tertiary chloride, because that carbon is attached to 3 other carbons. And so that's the best answer. Then it says, draw 2 other acceptable termination steps. All you need to do is look at all of the radicals you've drawn. We've drawn chlorine radicals, and we've drawn this radical. So for one termination step, you would show that radical reacting with a chlorine radical. Those two come together. And we'll get a small amount of the product from that termination step. The other termination step has 2 hydrocarbon radicals coming together. And that leads to a dimer. Looking something like this. Let me see if I can highlight a bond. And that is the new bond we just formed. So those are the other 2 termination steps. The question might also have said, draw all 3 termination steps, in which case you'd have drawn this one, and this one, and this one. Don't memorize this. This is just an example. but that's how you approach it. In one of them, you have the two halogen radicals coming together. They could be either chlorine or bromine. In the second one, you have a halogen radical coming together with the hydrocarbon radical that you hopefully correctly drew in the propagation step. You have those come together and you should get a molecule of the product that way. And in the third one, you have two of the hydrocarbon radicals coming together to form a dimer, meaning two of them stuck together. Well, I have to take a quick bathroom break. Let me just put this up here. And I will be right back. All right, I'm back. So this is showing the reaction of an alkene with HBr. That's a mechanism we went over a lot in class. So the reaction that leads to formation of compound B puts the bromine on the middle carbon. And in order to get that, we need to break the carbon-carbon pi bond like this. That's not the best arrow. So recall that in the first step of this reaction, you always break the carbon-carbon pi bond. And you point the arrow from breaking that carbon-carbon pi bond towards the hydrogen of the HCl, HBr, or HI. Then you also need to show breaking the hydrogen-halogen bond. And you should get a carbocation wherever you're planning on putting the halogen. So we took electrons away from that central carbon, and we left it with only 3 bonds. There's a hydrogen attached to this carbon too, but it is only 6 electrons around it. It is a formal charge of +1. This carbon over here is now a CH3. There were 2 hydrogens on that carbon to begin with, right over here. That's a CH2. And then a third hydrogen got added by protonation from the HBr. And then, in the second step, I hope this works. It sometimes doesn't like it when I draw single atoms like that. So far, it's letting me do it. So there's the halide ion that you get. I don't know why that's turning red. That's a perfectly good halide ion. And in the second step, remember that the halide ion attacks the carbocation and forms a new carbon-halogen bond. So you start the arrow where the electrons start. The arrow always starts where the electrons start. Arrows are used for showing movement of electrons, never atoms, never charges, only movement of electrons. And the arrow starts at the halide ion and ends at the carbocation. And from that, you get your compound B. And then there's also a way to get compound C. So now we need to show the bond breaking in the other direction. We break the hydrogen-bromine bond. And this time, the carbocation is on the end, CH2 plus. And then our halide ion will attack that carbocation. And you get compound C that way. You get a new carbon-bromine bond. So that bond right there is the new bond we formed. Now in chapter 7, we'll learn which of those two is the major product and which of those two is the minor product and why. And maybe you've already guessed. But we don't know that yet. That comes in chapter 7. So those are the two mechanisms. Any questions on that? So this page is on the same questions. Which of the following best describes compound B? Well, if you look carefully at compound B, that carbon is chiral. It has a bromine, a methyl group, a hydrogen, and a benzene ring, a phenyl group. So that carbon is chiral. So there's one chiral carbon. It will exist as one pair of enantiomers. What about compound C? Well, compound C is no chiral carbons. This is a CH2 over here. There's no chiral carbons. That carbon is not chiral because it's sp2 hybridized. So compound C is not chiral. Among compounds A, B, and C, if any are chiral, draw all possible stereoisomers below. If none are chiral, write none chiral. Well, the only chiral compound is compound B. And there's two stereoisomers that are enantiomers, one with the carbon-bromine bond being on a wedge, and the other with the carbon-bromine bond being a dotted bond. So those are the only two stereoisomers. And if they showed that, they got full credit. Good. Well, drawing energy diagrams in ChemDraw is very difficult. So I think I'll just rely on the answer key. Draw a qualitative energy diagram for a reaction that fits the following description. 2 steps, 1 intermediate, transition state between each 2 consecutive species, exergonic overall reaction. So you want energy of some kind on the vertical axis. Nowadays, I prefer to write delta G over here, because usually we're measuring in delta G. So energy on the vertical axis and reaction coordinate on the horizontal axis. And you'll show your starting material at some point along the way. There's going to be a high energy intermediate. That's over here. And then your product is going to be lower in energy than your starting material because it's an exergonic overall reaction. And then label these things the way we did in class. Delta G is going to be the difference in energy between the starting material and the product. So this is the product over here. That energy difference is the delta G of the reaction. The first activation energy, you can also call that delta G double dagger. Either EA or delta G double dagger is fine. And the activation energy is the difference in energy between where you start and where the transition state is. Recall that the transition states are energy maxima on the energy diagram. And so that the energy that you need to get over that hump is the activation energy. And then you get to the intermediate. And the second activation energy is this small amount of energy between the intermediate and the next transition state. So they're much closer in energy. It's just a little bit of energy you need to get over that activation barrier. And I didn't draw it the neatest in the world, but something like that was what we were looking for. The second energy diagram says 1 step with no intermediates, endergonic overall reaction. So that means the product is going to be higher in energy than the starting material. And I didn't line this up too well. This lower line should really be more like here. My eyes must have been a little cockeyed or something like that. So it's the difference in energy between the starting material and the product. That's the delta G of reaction. And the activation energy, once again, is the difference between where you start and the activation barrier, the transition state that you need to get over. There's no intermediates here. It's just 1 step. And you might recall that in class we said that you can tell the number of steps in a reaction from the energy diagram by the number of transition states. There are as many steps as there are transition states. No exception. That's always going to be true. So something like that was what we were looking for. I can't promise you it will be this same format in your exam, but you may expect there will be something on energy diagrams. We did spend some time talking about them in class, though we will hit them again in chapter 7 to some degree and in chapter 11 as well. Trying to grab this window and it's not letting me. Good. The next one is a very common type of question format on organic exams. You'll probably see questions like this on every exam from now on, in which you're given the starting material and reagents and asked to draw the product. And for full credit, the directions will probably be pretty much the same. You need to draw exactly one neutral organic compound. So no inorganic species, no intermediates, just the product. And we talked about the reaction of forming Grignard reagents in class. We said that if you're given an alkyl halide and told to react it with magnesium, then you get the magnesium halide. So you'll get MgBr. And then in class, we also said if you follow that up with reaction with water, then you will protonate that bond. So you'll go from MgBr or Mgi to H. And so that's going to be the product. You don't even really need to draw that hydrogen in. You could have just drawn the methyl group and that would be fine. So remember, when you're given an alkyl halide and told to react it with magnesium and no water following, then you insert magnesium into the carbon-halogen bond. You're not responsible for the mechanism. I'm not sure it's known. But if you're given an alkyl halide and told to react with magnesium followed by water, then you would first get the Grignard reagent, MgBr or Mgi, and then that bond gets protonated. We went over that in class and we showed the mechanism in class. That's just an acid-base reaction. So in the end, you wind up replacing the halogen with a hydrogen. And that hydrogen comes from the water. That was in chapter 10. The next one's also from chapter 10. Here I gave them a cuprate. And we said that the way to get the product, whenever you're given either a cuprate or an alkyl lithium reacting with copper 1 iodide, which gives you the cuprate. What you need to do is look at the group that's attached to the metal. We went over this in class. Look at the group that's attached to the metal. And then look at the alkyl halide you're given. And you want to attach the carbon that the halogen's attached to in the alkyl halide, that carbon to the carbon that's attached to the metal, either lithium or copper. And you just draw them and connect them. So we'll draw a cyclopentane. And then this is 1-bromobutane, so we'll attach 4 carbons over here. 1, 2, 3, 4. So once again, you take whatever is attached to the metal, whatever that group is that's attached to the metal, just copy it down. Whether it's attached to lithium or copper, just take whatever is attached to the metal and attach it instead to whatever is attached to the halogen in the alkyl halide that you're given.
Hello.
Question? Or no? So this is called a cuprate or a Gilman reagent. In the next reaction, we're treating this alkene with NBS and heat. And as we said in class, it's best practice unless it says excess, that it means one equivalent. However, in this case, it doesn't matter even if you use an excess because there's only one hydrogen that's allylic, this hydrogen here. So that's the only one that can get substituted for bromine from the NBS. So that's the product. And in the next reaction, we're given an alcohol. Actually, I'm going to get rid of the stereochemical issue. But in class, we said that if you have an alcohol and you treat it with thionyl chloride, SOCl2, it substitutes the OH group for a chlorine. So that's the best answer. And then finally, we're given this alkane and told to react it with Cl2 and light. This is a radical halogenation reaction. We have an excess of the alkane, so that means we'll replace only one of the hydrogens, and all 12 of those hydrogens are the same. So all we'll do is replace one of those hydrogens, and again, it doesn't matter which, they're all the same, with a chlorine. So that's a radical halogenation reaction like we talked about in chapter 6. And that's basically it for that page. So we had some chapter 10 reactions, and we had some chapter 6 reactions. But that's what it means to know a reaction. It means if you're given particular reagents that you've never seen before, you understand what the reagents do. So knowing a reaction does not mean memorizing the examples from class. I can almost guarantee you the examples from class will not appear on the exam. You're going to have to apply that information to a situation that's similar but not identical. The best analogy I can give you is when you learned high school math and you learned the, what was that called? Quadratic formula. Yes, there's some memorization involved. You had to learn that x is, what is it, minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So you had to memorize that formula, but you had to know what to do with it. You had to know how to apply it, even when you were given a quadratic equation that you've never seen before. You had to apply the information to a new situation. And that's the same type of knowledge that it takes to succeed in organic chemistry. So that's about the best advice I think I can give you there. Oh, any questions on any of those reactions? Here's another radical chain reaction. I went easy on them that year. I just gave them cyclohexane. All 12 hydrogens are the same, so it doesn't matter which you take. So recall in the initiation step, the halogen molecule splits up into two halogen radicals. So you get two of these. And then in the propagation step, we start with the hydrocarbon we're given. It actually doesn't matter which of the hydrogens we take in this case, they're all the same. If they're not all the same, then you look where the halogen is in the product, and that will show you which hydrogen to take. You take whichever hydrogen that leads to formation of that halide product. Here it doesn't matter since it's cyclohexane and they're all the same. So, once again, we react the single electron on the halogen. And don't memorize that it's Cl, it could just as easily be Br. And we take one electron from the carbon-hydrogen bond and the other electron from the carbon-hydrogen bond goes onto the carbon and makes a hydrocarbon radical. So you get this radical that then reacts with the halogen molecule, and one electron from the halogen-halogen bond combines with the single electron on the organic radical. The other electron in the halogen-halogen bond goes on the other halogen atom, the one that does not get attached to the carbon. And you will get the product and also another halogen radical. And then in the termination step, in this case, I gave them a choice. Let's draw all three termination steps. In one of them, the two halogen atoms come together. Make a halogen molecule. In another termination step, a halogen radical combines with an organic radical. And you should get a molecule of the product. And then lastly, we take two of the organic radical and we combine them together to get two of the organic groups attached together. Let me move that somewhere where we can see it all. So that's how you do it if you're asked for all three termination steps. If it doesn't say you have to do all three, then you don't have to do all three. You can just pick one of them. But if it says to draw all three, that's how you handle it. Again, be very systematic. Be sure that you get all of the possibilities. Okay. The next one says to find the ratio of the products if only statistics or random chance plays a role in product distribution. So this doesn't require you to know anything about the relative reactivities of primary, secondary, and tertiary hydrogens. So we did a few examples of this in class. All we need to do is count hydrogens. So for that first product, you'll notice we have our halogen attached to this carbon. That means that we took away one of those hydrogens. And that's a CH3. There's 3 hydrogens attached there. So that's the number you put in, is the number of H's that you can take in order to get that product. The number of H's that you can replace with the halogen in order to get the product shown. And there's 3 of those H's. And the next product to the right, we're attaching our bromine over here. And there's only 1 hydrogen attached to that carbon. So that's the only hydrogen that we can take in order to get that product. Again, we're not taking into account radical stability at all. We're just assuming only random chance, only statistics governs product formation. In this product, our halogen is attached to this carbon. That means we took one of the hydrogens attached to this carbon in the starting material. That carbon has 2 H's attached. So that's the number we put in the blank, 2, for 2 H's. And then last but not least, the bromine's attached over here. That means we took an H off of that carbon and replaced it with a bromine in the propagation step of the halogenation reaction. And so that carbon is right over here in the starting material. That carbon has 3 H's attached. And you can take any of those 3 H's, you can replace any of those 3 H's with bromine and get this product. So since it's 3 H's, we put 3 in that spot. It's just counting hydrogens. That's how you answer a question like that. Sure, you could do percentage if you really wanted to, but why go to the trouble? And then in this one, we already did a problem like this. This is just another example of the same type of problem. So all we'll do is we'll systematically replace hydrogens with bromines. The reason I know to use bromine is because I'm given Br2. If I'd been given Cl2, I would replace them with chlorines. It says draw exactly 4 of the possible products. You could also attach the bromine over here. You could also attach, whoops, the bromine over here. Or you could attach it over here. I'm just going down the chain. And there are several others. You could attach the bromine over here. Or over there. Or you could attach the bromine over here by taking away that hydrogen, or you could attach the bromine over here. So there are about 7 possible answers, and we accepted any 4 of them. So again, if you have one of these isomers questions, I'll say it again, just be systematic. Just move down the chain, replacing H's with halogens. Oh, that's the end. We actually got through it all. All right, we still have about 15 minutes. I'll make up some other questions. Um, that's a reaction we talked about in class. As to the wording of the question, it would say something like, draw the major organic product of the reaction. Just to clarify, I usually say something like, for full credit, your answer must be caps lock exactly one neutral organic compound. And there might be other directions on showing stereochemistry or like that. Put an iodine over here. We'll treat it with magnesium and diethyl ether. What else? I really wasn't expecting to get through all that.
Professor, if you're taking question requests, could you also go over an oxidation reduction problem?
Okay, sure. I should have done that to start with. Yeah, we have plenty of time. Actually, I can turn these into oxidation reduction problems. So recall that phosphorus tribromide converts a primary or secondary alcohol to the corresponding bromide. It just substitutes the OH for bromine. You're not responsible for the mechanism. And recall when you treat an alkyl halide with magnesium and it's not followed up by water, then you insert the magnesium in the carbon-halogen bond. Most likely the halogen will be either bromine or iodine. Let's make it a little harder at least. And then this is treatment of an alkene with HCl or HBr. Remember, you turn the double bond into a single bond, and one of the carbons gets the halogen and the other one gets the hydrogen. So really, as it's currently put, I would have to accept both answers. Maybe it's not a very good question. What would be a redox question? By each equation, write oxidation, reduction, or neither as appropriate. I'd probably phrase it a little better than that. But this is just coming right off the top of my head. So that's one. We'll do that question we just did. Let's go crazy and do a 7-membered ring. Let's say we did an NBS reaction. And you might or might not be given the reagents. You might be given just arrows, or you might be given the reagents over it. Doesn't really matter. You get the answer by comparing the starting material to the product. Let me do one more. Was hoping that would happen. All right, so let's look at this first one. What are the changes that take place in the molecule? Well, we have a carbon-oxygen single bond turning into a carbon-oxygen double bond. And so one of the things we said was whenever the bond order increases, that's an oxidation. The other way you can get that this is an oxidation is we're going from one carbon-oxygen bond to 2 carbon-oxygen bonds, and we've increased the number of bonds between carbon and an electronegative element. We've increased the number of bonds between carbon and an electronegative element. That's also an oxidation. Now, in this reaction, we've added HCl across this alkene double bond. That's something you should be able to draw the mechanism of. We went over several examples of that mechanism in class, and we did some tonight as well. So on one carbon, we're attaching an electronegative element. But on the other carbon, we're attaching a hydrogen. This is a CH2, and this is now a CH3. So we have an additional bond to hydrogen. So we've increased the number of bonds to an electronegative element, which is oxidation. We've also increased the number of bonds to hydrogen, which is a reduction. So those two cancel out. This is neither a reduction nor an oxidation. It's right in the middle of the two. What's happening in the next compound? Well, the change that takes place is we go from a carbon-carbon double bond to a carbon-carbon single bond. The bond order has gone down. So that falls in the definition of reduction. What about the next one? Well, we've replaced a carbon-hydrogen bond with a carbon-bromine bond. So we've reduced the number of carbon-hydrogen bonds, which is an oxidation, and we've also increased the number of bonds between carbon and an electronegative element, which is also oxidation. You could look at it either way. Whichever method you use, you come up with the same answer, oxidation. And what about that last one? Well, we're going from a double bond to a single bond. The bond order is going down. So that falls under the definition of reduction. You could also look at it like this. You've got 2 bonds between carbon and an electronegative element in the starting material, and only 1 bond between carbon and an electronegative element in the product. So the number of bonds to an electronegative element has gone down. That also falls under the definition of reduction. Make sense? Well, we still have 3 or 4 minutes. Is there anything else you want to see?
Can we go over Rye and Psi faces?
Ray and C phases.
Yeah. Yes.
Let's consider this compound. And we'll figure out whether we're looking at the Ray face or the C face. So what we'll do is we'll prioritize the 3 groups attached to that central sp2 hybridized carbon. The oxygen is first. The carbon in the benzene ring is second. And the carbon in the methyl group is third. Looks to me like that's a left turn. That means we're viewing the molecule from the C face. C like for S. If we were looking at it from the other angle, then the oxygen would again be number 1. The benzene ring would be number 2. And the methyl group would be number 3. That's now a right turn, so in this case, we're looking at the molecule from the Ray face. So that's how I would explain that. I'm trying to think of one last question. Let's do this mechanism. I just want to make sure we practice the 2 mechanisms that we learned in chapter 6. So first thing you're going to do is draw your starting material and the hydrogen halide that are given. Then you show an arrow starting at the pi bond and ending at the hydrogen of the hydrogen halide. And then you need another arrow breaking the hydrogen-halogen bond. That gives you a carbocation. And just for the sake of clarity, there are now 2 hydrogens attached to that carbon, which you don't have to draw if you're using line angle drawings. That's the beauty of line angle drawings. You don't have to show the H's. You can, if you find it confusing to leave them out, you can draw them in. No harm done. So in the next step, the halide ion attacks the carbocation. So remember, this reaction has 2 steps. And you show the halide ion attacking the carbocation. And that gets you straight to the product. So if something like this is on the exam, plan on it starting with an alkene you've never seen before. But know the 2 steps of the mechanism. First, an arrow starting at the pi bond and moving towards the hydrogen of the hydrogen halide, breaking the hydrogen-halogen bond. That's the first step. And you make a carbocation. Be sure you put the plus charge on the right carbon. In this case, it doesn't matter since all 8 carbons are the same. And then in the second step, the halide ion attacks the carbocation and you form the new carbon-halogen bond. So it's a 2-step process. That was the sample polar reaction we learned about in chapter 6. Good. Well, with that, we're pretty much out of time, unless there's any last questions. Looks like people are already leaving. That's fine. Good. So on Wednesday, we'll start chapter 11. That material will not be on this exam. That will be on exam number 3. But it's the only time I'm going to teach on it, and it's pretty important material, so you don't want to miss that class. Good. Well, enjoy your remaining day of break. I'll be thinking of you when I'm sitting in meetings all day. And I will see you all on Wednesday.
Thank you so much for your time, Professor. Have a good
No
week.
problem.